Hi everyone, welcome back to the channel. Today we're continuing our journey through difference equations, and specifically we're going to move into coupled difference equations. These show up in economics when two variables evolve together over time, influencing each other. For example, capital and output, or price and quantity, or income and consumption. The reason this topic is so important is that real economic systems are rarely isolated. One variable doesn't change alone. When one thing moves, something else moves with it. Sometimes in the same direction, sometimes in the opposite. So today we're going to look at what coupled systems are, how to make them in matrix form, and how to find the equilibrium, and then how to analyze stability and long run behavior. We'll take it slowly and visually, so don't worry if this is your first time seeing this. By the end of this lesson, you will be able to look at a system of two linked equations and actually understand what is happening over time. So let's begin. Uh, we'll be solving questions which follow two formats. So format number one is a system which is homogeneous, and format number two is a system which is non-homogeneous. So it will have a homogeneous part, and going to have to solve for the particular equation as well. uh, but before we do this, we want to understand how to do diagonalization, because that's one thing which really helps us to solve coupled equations. So, I want to discuss firstly, before moving on to this, how we can use diagonalization to solve coupled equations. So, for instance, let's suppose we have a matrix A, with the first row being 4 1 and the second row being 2 3, and we want to find the eigenvalues and eigenvector of this matrix. An eigenvector is called V, while an eigenvalue is lambda. Let me write that here as well. So lambda is an eigenvalue, while V is an eigenvector, and they both have to basically satisfy this definition. So what is A minus lambda I? I being the identity, will get a 4 minus um, lambda, 1 remains there, 2, 3 minus lambda. So I want to take the determinant and then put it equals to 0. The determinant is a 4 minus lambda into a 3 minus lambda minus 2 is equals to a 0. Let's open this up. 12 minus 4 lambda minus 3 lambda plus lambda square minus 2 is equals to a 0. Then we're left with lambda square minus 7 lambda plus 10 is equals to a 0. We need to factorize this. 5 2s are 10, and 5 plus 2 will give us a 7. So let's do this. Lambda square minus 5 lambda minus 2 lambda plus 10 is equals to a 0. So we are going to basically end up with two roots here. One is going to be lambda is equals to lambda, we can say one eigenvalue is 2 and the other eigenvalue is a 5. So the diagonal matrix basically has these eigenvalues on its diagonal as its diagonal entries. So for instance, I can write the diagonal matrix here as 2, 5 on the diagonal, and then 0 everywhere else. So now we want to find the eigenvector V1 associated with the eigenvalue lambda 1. So what we're looking for is, we want a V1 such that it gives us lambda 1 V1. So basically we want to solve this system. So what is this matrix going to be? We are going to get a 4 minus 2, 1, 2, and then we have a 3 minus a 2, 0, 0, where v1 is a two-dimensional column vector. So what is the augmented matrix here? We're left with 2, 1, 2, 1, 0, 0. And when I do row 2 minus row 1, I'm left with 2, 1, 0, 0, 0, and 0. This, since the last row is all zeros, therefore the value of y is just any variable, for instance t. So there are infinite many solutions to this system. The first equation says 2x plus y is equals to a 0, where we are taking y is equals to a t. So x is going to be a minus t over a 2. So if we take t, the value of t as, let's take it as, did I write it correctly? Yeah, if I take it as, I don't want a fraction though, so let's take it as 2. Then I'm going to be left with a minus 1 value as x. So this means that if I take the value of y as 1, then I'll be, or 2, sorry, I took it as 2. My bad. Then I'll be left with the x, which is a minus 1. Or I could actually, if I want a positive number there, I could also take this as, I can write a minus 2 here and a positive 1 there. Maybe that's, it's actually the same thing. So let's just stick with the minus 2 here, so we get a positive 1 there. It's actually the same thing. It's going to give you the same answers. Okay. Let's find the eigenvector v2 associated with lambda 2. We're going to have a 4 minus a 5. 1 remains there, 2 remains there, and then a 3 minus a 5. And then we have a 0, 0 here. This is a minus 1, 1, 2, minus 2, 0, 0. We're going to do row 2 plus a 2 row 1, and then we have a minus 1, 1, 0, 0, 0, 0. Again, infinitely many solutions. A minus x plus y is equals to a 0. That means x is equals to a y. So if y is equals to any constant t, we take it as 1, then x is also equals to 1. So the next eigenvector is a 1, 1. So the D matrix has lambda 1 and lambda 2 on its diagonal entries, while P matrix has v1, v2 as its column vectors. So let's write this out. We have a 2, 0, 0, 5 here, and we have a 1, minus 2, 1, 1 here. So now we have enough information. Actually, we can also find, sometimes it comes in handy, the inverse of P, which is going to be a 1 over 1 minus 2, which is a 3. And then we switch these and we change the sign here. So it's quite handy if we have the inverse as well. So this is all the information we need to solve, what am I saying, to prove that P inverse of A P is going to give us the diagonal matrix D. So these matrices basically satisfy this equation, which we're going to use when we solve the system. So this comes in handy. Okay, moving on. Suppose we have this system and the question says you need to find x and y, and x, the future value of x, not only depends on its own past value, but it also depends on the past value of another variable. So basically these are interlinked. So that this is where diagonalization helps to solve these coupled equations. So when I write this out, at first I need to convert it into matrix form, which is quite easy because we can just write the constants attached to each variable. And I can say this is basically in this form where z is a column vector which represents this. This is the matrix A and this is a column vector. So this denotes the time t and this denotes the future period. So we have this matrix A, we've already found out the diagonal matrix and we know the matrix P, we calculated it already, and we also calculated the inverse, and we know that all of these three basically satisfy this equation. So let's start by solving such a system. So there's a change of variable technique. I want to assume or take basically that that zt is P matrix multiplied by mt, where I can say mt is basically a column vector, where I can just say it can be, you can take any letters, it doesn't matter. And I can call this my equation 2, whereas my equation 1 was the one that we have right here. So this is my equation 1 right here. So what I want to do is I want to substitute equation 2 into 1. So I want to put equation 2 or substitute equation 2 into equation 1. Okay, so since equation 1 was where I'll just write it again, where equation 1 is why won't this go away? Here we go. Zt is equals to a, actually I think it was zt plus 1. Zt plus 1 is a zt. This was the first equation. So let's put it in. We have a p mt plus 1 will be a p mt. So multiplying the inverse of p from on both sides, I know that p inverse of p is simply the identity matrix. So I get the identity matrix here, and I'm going to be left with p inverse ap on the right side. Therefore I get mt plus 1 here, I get the diagonal matrix here and mt. The benefit of doing this is that this collapses to a very simple first order difference equation. So let's show this. We've just said that mt plus 1 is equals to dmt, right? So where mt plus 1 was small mt plus 1, small nt plus 1, this was the column vector right here. And then we had the diagonal matrix, which was a 2 0 0 5, and then we had mt nt as the column vector. Now if I open this system, it becomes, when we multiply row into column, it becomes 2mt and 5nt. So this is, we've already covered this in the first lecture, but this is a simple first order difference equation, and I know the solution of this is mt is equals to m initial, m at time t at t is equals to 0, and 2 power t. And what about nt plus 1? We have a 5nt, and therefore this is going to be, I'm going to get nt is equals to n naught 5 power t. Okay, final step. We had assumed that for a change of variable that zt is basically p mt, and this is what we wanted to actually find, right? We were asked this. So what is the matrix? We get an xt and a yt, and the P matrix was the matrix consisting of the eigenvectors, which is a 1, -2, 1, 1, and mt, we just found out mt, which was a m naught 2 power t, n naught 5 power t. So therefore, we have the following solution: xt is equals to m naught 2t plus n naught 5t, and yt is equals to -2 m naught 2t plus n naught 5t, where m naught and n naught are unknown, and therefore we need to find them. But we can only find them if the initial conditions of this equation was given, right? So you can find uh, uh, m naught n naught only if the value of x naught and y naught is given. So if x naught and y naught is given, only then you can find m naught n naught. So in the above equation, what if I take t is equals to a 0, and suppose the question has told me the initial value of x is a 1 and the initial value of y is equals to 0. So what does this equation become? This becomes, at time t0, this will be x0, y0, and then we are going to have a 2 power 0 and 5 power 0. So what does this become? We are going to be left with this. We have a 1 here, a 0 here. Anything power 0 is actually equals to a 1. So at this point, you can either use row operations, or you can use the Kramer's rule, or you can just find the inverse and multiply it and get the answer. It's your choice. So let's go on with just multiplying both sides with the inverse, because we already had the inverse. So let's multiply both sides by the inverse. So multiplying the inverse of this matrix on this side, so I get the identity matrix. So identity matrix here, and I have to multiply the inverse over here. So I am basically taking the inverse and I am going to multiply the inverse of this matrix on both sides. So this is a 2 by 2 matrix, so the inverse is fairly easy. So I get a 1 by 3, 1 minus 1, 2, 1, and I want to multiply it by a 1, 0, and therefore I get a 1 over a 3, 1, 2, and then I'll get a 1 by 3 and 2 by 3. And there you go. We have our final answer. So we found out the unknowns. All I need to do is just write this down. So I found the values of m naught and n naught. So xt is going to be a 1 over 3 2 power t plus 2 over 3 5 power t, and the value of yt is going to be a minus 2 over a 3 2 power t plus 2 over 3 and 5 power t. And we're done there. So I hope this was fairly easy to understand. So the thing is that when you're doing a master's degree in economics, mostly the question is not, is not in given with actual constants given. So for instance, in this question, we had these numbers 4, 1, 2, 3. But when you're doing a master's degree, you'll most probably be faced with a question in which this is not actually given. So you'll just be given variables. So for instance, what I'm saying is, suppose they give you a question like this. So they give you a question in which they say, suppose yt is equals to alpha 1 yt minus 1 plus alpha 2 zt minus 1 plus some constant a naught, and zt is equals to b1 yt minus 1 plus b2 zt minus 1 plus b naught. So basically this system is, if I represent xt as the column yt zt vector, then if I convert this in actually let's just write this out. The first column here is a yt zt, and the matrix form will be alpha 1 alpha 2 beta 1 beta 2, and then we have a yt minus 1 and zt minus 1 plus an alpha naught beta naught. So we have this system. We have I've already used z. So xt is equals to a xt minus 1 plus some constant g. There are two kinds of questions, like there could be a simple format, like so the format one could be they've just given you the homogeneous system, so a question might appear in just this form. Or there could be the next format in which they don't give just the homogeneous system, they actually give the whole system like this. So these are two possibilities that you might face in a question. So let's just do the first format, because I know I'm going to have to solve it again to find the homogeneous system here. So let's just start by doing format number 1, and basically this is the homogeneous solution. So solution to the homogeneous system. So so remember now that I don't really have any because I don't have any numbers, so I can't actually find the actual values of the eigenvalues and eigenvectors, right? So what I'm going to write out for the examiner is simply the procedure. I'm going to say that a minus lambda I, if I take the determinant and I put it equals to 0, I am going to get, since this is a 2 by 2 matrix, I'm going to get two eigenvalues. I'm going to say I'm going to get a lambda 1 and lambda 2. So I'm just solving this generically, and I know that these will appear on the diagonal of the diagonal matrix. So I'm just going to put it like this. So I don't know these answers because I didn't know what matrix A constants were. Okay, then I'm going to tell the examiner that when I put lambda 1 into this, and I solved it. So I got this value of this eigenvector was, let's suppose, 1v. Okay, just say this was v1. Okay, so this is going to help me find the vector, the matrix P. So the first eigenvector is 1v, and suppose I put in the second value, the lambda 2, to find second eigenvector. Let's suppose the second eigenvector is a 1 and a u, because I suppose I just wanted to avoid fraction. So I am left with this equation, this vector. So now we are in a place where we can solve the system because we have everything that we needed. So what are we going to assume? I'm just going to say, so assume that xt is equals to pmt. So basically we're doing a change of variable. Okay, and I'm going to just multiply. I'm just going to put this in the equation. Xt is equals to a xt minus 1. So I'm going to get a p m t is equals to a p m t minus 1. So again mt is equals to d mt minus 1. So what do I have? I have an mt nt is equals to the diagonal matrix, which was a lambda 1 0 0 lambda 2, and this was mt minus 1 and nt minus 1, and I multiply this row into column. I am left with lambda 1 mt minus 1 lambda 2 nt minus 1, and therefore this system collapses to a very simple first order difference equation. And we know from the first lesson that the solution to this is going to be m naught lambda 1 power t, and when we have nt lambda 2 nt minus 1, we have and nt is equals to n naught lambda 2 power t. So now we're in a place where we can find the final solution, because we know that we had assumed x is equals to pmt. So therefore x is equals to pmt, where p was a 1v1u and mt, we just found this out. This was our mt, and therefore we have the solution to the homogeneous system, because I know xt is basic. What was xt? Xt was basically yt zt. So therefore yt is equals to v m naught lambda 1 t plus u n naught lambda 2 t, and zt will be given as m naught lambda 1 t plus n naught lambda 2 t. Okay, so suppose now we have a question which is given in the second format, right? So suppose you have a system where you've been given a question that looks like this: xt is equals to xt minus 1 plus g. So in this, remember the final solution was like the general solution, what did we write it at? We know that the general solution to the system is going to be equal to the homogeneous system plus the particular solution. We've already written out the homogeneous solution, which was this above. So like what I can write this as, that the general solution was, so far it was this was the general homogeneous solution, and we don't know the particular solution as yet, so we just need to find the particular solution. As before, we are going to say that the particular solution, since G is a constant, is a column vector which has constants in it, therefore I can say that the vector xt is basically constant solution. So basically I'm saying that we have an x t is equals to a x t minus 1 plus g, so this becomes an x bar. We get an a x bar plus g, then I get identity minus a x bar is equals to a g. So therefore x bar is identity minus a, whatever this matrix was, the inverse, and we multiply it by g. So this is basically going to give you a column vector, because if this is going to be a 2 by 2 matrix and this is a 2 into 1 column vector, so therefore the answer should be a 2 into 1 column vector. So what I can say is that the constant, I can assume that the solution is some z bar y bar z bar, and therefore now we are in a place where we can just simply write down the final solution. However, if you want to do it, like we stated before in the previous video, that in order to find the homogeneous solution, you have to basically solve the system where xt is equals to a xt minus 1, and then what you have to do is that you have to take a trial solution, and then that's your guess solution. So you basically make a guess that this is some matrix b lambda power t, and you substitute it back into the equation, so you're left with a b lambda t is equals to a b lambda t minus 1, and therefore you get an a b lambda t minus 1 minus a b lambda t is equals to a 0. And then when you take you can take b lambda t as common, so then you will be left with I wonder, matrix multiplication isn't commutative, so I think I'll have to put b on the right side. So because in matrix, like if you multiply matrix a multiplied by b, it's not equals to b multiplied by a. So I think what we should do is I'm going to write this like this, and I'm going to put matrix b here, because identity into a b is actually the same as b into identity. That wouldn't matter, but I need b to multiply here on the right side. Anyhow, I'm just blabbing on. The lambda and beta matrix, since it's not equals to the 0, therefore this is where we get the characteristic equation. We say like that this determinant, we take the determinant and we put it equals to 0. This is what we call the this is the characteristic equation, and this gives us the value of the eigenvectors. So basically when we solve this, we get, sorry, my bad, I meant eigenvalues. We get these two. Anyhow, going back to the way we all have already solved it, we had this solution, the homogeneous solution already with us. So this was the main equation, and this was the homogeneous solution, and I can write this, that this is the homogeneous solution, and the particular solution turned out to be a y bar, and the particular solution for z was a z bar. Therefore the final solution for yt would be this plus this, and the final solution for zt would be this plus this. And there we have it. I think it was a zt, and this is our final solution. I hope this video has already become very long. We just want to state that the system is stable as long as the absolute value of the eigenvalues, absolute value of the eigenvalues is less than 1. And in the next video we're going to talk about the saddle path equilibrium. I hope I made this topic easy for everyone. These notes will be available in the comments. I'll give the link to these notes. Bye.